Good morning, and thank you for giving me the opportunity to speak with you all today. For those of you that don't know me, I'm Mike Picco, founded Picco Engineering in 1992, and prior to that, worked with a fabricator and installation company, one of the biggest in Toronto. We did several large projects, and that's really where I got my experience in the industry. We're a structural engineering firm with three main pillars: structural engineering, residential engineering, and our core business is really the stone, anything to do with stone. So since I started in 1992, I've had the opportunity to visit quarries all over the world, worked on some fascinating projects, spoke at several conferences. I was the president of the Natural Stone Institute in 2020. And as a Canadian, I still play hockey a couple of times a week in the winter, so that's part of who I am. Today, we're going to talk about several things associated with stone. Why dimension stone and why use it? What is dimension stone? And then we're going to look at 5 key ingredients to what we feel is critical to a project success. And then we'll look at a few case studies. I'm going to be packing in a lot of information, so I'm going to go through really quickly and hopefully give you a bit of time at the end of the presentation for questions. We're going to look at various types of stone cladding, look at some examples, critical factors influencing a project success, brief overview of material selection and what goes behind that, and then look at structural integrity backup, how we anchor the stone to the building, and discuss some important other essentials as part of that process. So our 3 pillars of our business, so we're focusing on stone today, and I'm really going to focus on the stone aspect, not the whole envelope, but really from the structure outwards and how we work with stone, and really focus on that as the presentation goes on. As far as what we do with our services, anything and everything related to natural stone, right from sourcing material, testing, design assist at the early stages of projects. We work on restoration projects. Our core business is really doing the engineering shop drawings and fabrication tickets, but we do touch all aspects of the business. So let's get right into it. I think it's important we ask the question, what is dimension stone and why use it? Well, dimensional stone is quarried natural stone that is sourced, cut, and finished to specific and true custom specifications. So unlike going to your local building supply place and buying a skid of stone that you install, in dimension natural stone is detailed, cut, and fabricated to a specific location and placement on a building. So every stone is numbered, engineered, and detailed. That's the difference between dimensional cut stone and just a stone facade. As far as why use stone, if it's not the most sustainable, it's one of the most sustainable building materials out there. It's low embodied carbon. It's a 1 ingredient product. You take it out of the ground, you cut it, you shape it, you put it on a building. It really doesn't get much more sustainable than that. It's got history. We've got centuries of use, so we know it's a sustainable product from longevity. It's got strength characteristics. It's versatile, can be shaped, especially now with new CNC technology. You can really get very creative with its use. And at the end of use, you can recycle it, repurpose it, reuse it, or simply put it back in the earth where it came from, and it's back home where it started with very little impact. The Natural Stone Institute did develop some sustainability standards that were in the industry at first and now have been accepted by ANSI, and it is an ANSI standard, which is the Sustainable Production of Natural Dimension Stone, and that's available on the Natural Stone Institute website. And they're also working on developing EPDs and other tools for architects and designers in the use of natural stone. So let's look at the 5 key ingredients that we feel are very important in developing a successful project. Collaborative plan and team, probably the most important. Project architecture, design development, material science and sourcing, the fabrication aspects, and then the installation and construction. And we'll get into a little more detail on each one of these. So we feel right at the beginning of the project, it's extremely important that you assemble the proper stakeholders, proper people that have the experience that's aligned with the project that you're working with. Obviously, the more complex the project, the more important it is to making sure that everyone has the proper skill sets required to execute on the job. Collaboration is important at the beginning. How are we communicating with our technology and BIM tools? Who's going to hub it? How are we going to effectively communicate with each other? And all this needs to be established very early on in the process. The architectural development and design development, the architect comes up with a concept and a vision, and it's our goal to try and make that vision come to a reality. And that's really what we're trying to do. Early on in the process, which is usually through a design assist process, we look at all the limitations or all the opportunities on the design and vision of the architect. Is the proper stone being used? Are there other options available? Is the panel size too big at the stone that's been selected? So all these things can be vetted during the early stages of the project. And look at also relationship with the structure. What does the structure need? Are there other elements that need to be incorporated into the structure to really facilitate the installation of the stone? When we look at the material cut, how is the stone being cut? I've got photos coming up, but the stone comes out in blocks, and it can be cut vein cut or flurry cut. So with the vein or perpendicular to the vein. And that can yield very different aesthetics to the stone, but also very different physical properties that we have to work with, depending on how that stone is cut. And that needs to be vetted through the testing process. The wall cavity, what's the optimal wall cavity? And that's really predicated on the envelope requirements. Is it a rain screen? Is it an open joint system? Is it a closed joint system? Where's the insulation? Is it outboard, inboard? And these are all things that need to be looked at. And then once that's established, what's the optimal cavity space to establish that from an envelope perspective? And how do we ensure that it's economical from an installation perspective as well? We look at the structural backup. What are the opportunities there? Obviously, from our perspective, concrete and CMU are the best because it gives us an unlimited facade to put anchors into. We're not limited on, and it gives us good capacity. Steel subframes or aluminum subframes are also an effective option on some projects where we engineer and detail those to align with the stone modulation and where we need structure. Metal studs is very often what we're working with. It seems to be the most common building facade right now, whether it's infill studs or whether it's structural studs. The limitations with those are we either need to go with a system or we need to provide some kind of bridging channels or bridging structure because it's unlikely that the studs are going to align with our connection requirements. So that's the least preferred, but probably the one that we're most using right now. The stone jointing and modulation is also something that's very critical that can impact, again, depending on the stone that's selected, what are the limitations on sizes, what's the optimal size, where are the joints located in relation to the structure, what do we need to accommodate that. With very large panels, you usually need multiple connections because we are always trying to keep the stone very thin to obviously optimize the use of the material and keep the weight down. So multiple connections sometimes can add some complexity to the installation. The stone support strategy, is it being individually supported where each stone is anchored to support the load, which is most preferred and most often done on facade installations, but you can also stack stones. So you can have structure, whether it's at the floor slabs or at the base of the building, and you can stack stone. Usually requires the stone to be a little thicker in those cases. But again, that could be a strategy in some projects that could be a very effective way to support the stone. Anchoring strategies is another thing. We have various options available to us. Individual, on the left there, you can see stainless steel clips and angles that are very, very commonly used. Still today, there's various systems on the market that can be anchored back to the structure. that are very common as well. And here, just to name a few that are out there, and we've used all of these on different projects. They all offer different advantages and disadvantages depending on the type of installation that we're looking at doing. The material science in the sourcing. Why are dimensional stones engineered, and why is the requirement of engineering? Obviously, the location of the building and the impact of the environment on it. What are the environmental conditions that we're dealing with could often determine whether a stone is acceptable or not in a certain environment. We often get, samples of stones sent on to architects for projects that, we use this stone in Florida and it was perfectly fine. Well, it may not be fine in Chicago or somewhere that experiences high degrees of thermal cycles and freeze-thaw cycles over the course of the year. So understanding that and its relation to the selection of the stone is very important. The variability of the stone, what stone is being used, what's the extraction process, what are the physical properties. You can see here different sizes of blocks and different extraction methods that are all used on building materials, and you can see the various limitations that you may have depending on which product is selected. Limestones, as you can see in the top left picture, are usually natural beds of limestone where the stone comes out in a certain height. So you can see, as we mentioned before, vein cut or flurry cut, you can have very limitations on your height if you're using a vein cut for that stone, but in the flurry cut, you can get much larger panels. Again, understanding all this is extremely important. Other aspect is your local building codes, project specifications that will also drive many of our decisions early on. Sourcing, where does the material come from? Understanding that is extremely important. There's a big problem in the industry with the name game. People change names on materials to try and protect where it's coming from to eliminate competitors for bidding on it. So really drilling down and understanding where the stone comes from, the chain of custody, implementing QA/QC process, whether it requires dry lays or mock-ups or physical mock-ups, but really understanding that process is very, very important in the success of a project. Testing. We very often get historic testing on material, which is great for doing our preliminary analysis. But we need more than that. We need to understand the variability of the materials. Some materials are very, very consistent in their physical properties and others vary. So we've got just to demonstrate that as a quick example here, we've got two materials here, both with 1,000 PSI strength. Material A, 1,018 PSI, material B, 1,022. So if we were to get those average flexural strength from a supplier, we would think they're both the same material. They're both around 1,000 PSI. We could design them the same. Well, with a natural stone, it's crucial to understand the variability. You can see by the charts there, material A has an average flexural strength, of 1,018, with the lowest value being around 900 and the highest value being around 1,100. Whereas material B has an average of 1,022 with values as low as 600 and as high as 1,400. So we can't design these two materials the same way. We have to apply a much higher safety factor into our design and our calculations for material B. You can see the coefficient of variation on A is 7, on B it's 29. So we need to work with a much higher safety factor on material B in order to make it work and make it safe. And also understanding these properties allows us to design the most efficiently and safely at the same time. Stone fabrication is another very important thing to consider. Who's fabricating the stone? What are their capabilities? What are they? What technology do they have in their shop? What equipment do they have? Understanding that is also very important, which very often can yield very different pricing depending on who you're dealing with and depending on the technology available they have for their fabrication. Here's just a quick example here of some double curved column covers that were being fabricated. And, you can see that this has a 5-axis wire saw cutting these and nesting all the pieces into each other, a very efficient way to fabricate these pieces. If someone doesn't have that saw, which was the case in this, they had two prices. One was about 4 times more expensive than the other. Well, the other fabricator was going to cut rectangular shapes and then create those shapes individually from each piece. They required 5 times more the amount of material because they didn't have the technology to be able to fabricate in this fashion. So understanding the fabricators that you're working with natural stone and their capabilities are also very important. And how do they need the information sent to them? Most of them are all CNC now. They all have digital capabilities. So it's very common that we share digital files of the fabrication pieces required. But there's always a paper copy or a physical ticket that goes with it as well. That usually travels with the piece, because regardless of how much technology they have, there's always a certain amount of handwork or handling of the piece before it's finalized. So it's important to have a paper copy that usually travels with the stone down the production line. Quality control and dry lays are very common. The photo on the left is probably a dry lay that's really there for shading or any impurities or imperfections in the stone that may be detected, whereas the one on the right is a full-scale dry lay of all the pieces that are checking fitment, fabrication, color, and everything before it's done. Now, it is a little bit of an expensive process, but it's way more expensive if a piece is cut wrong and it's found out when it's on the job site, when everybody's there, and then you got to wait 6 weeks or 8 weeks for a piece to be refabricated. So this is very often part of the process in order to eliminate any issues downfield. Communicating with the job site and how the installers and fabricators and logistics sometimes will do color coding of different parts or components of a project. This is a small private mausoleum, and you can see how we've color coded different parts of it in order to facilitate packaging, shipping, kind of phasing the production, and also aiding in the installation. And there's the finished product. That's completely structural stone throughout. There's no structure other than the stone in that building there. Communication and level of detail of communication, ensuring all the stakeholders are at the same level, same expectations on how we're going to communicate and build our models. Is it required to go to the level of detail? If it's a small project, why waste the time on it? If it's a complex project that requires it, then certainly. And this is actually the Museum of Human Rights that Luca mentioned before. And you can see here how effective a digital model that to this level can be for all stakeholders in it. You can clearly see that corner and the model for it and all the connection components and how it's reflected on site with the real products there. This is the Museum of Natural History, the Gilder Center. We were involved with some of the complex pieces. We didn't do the main part of it, but they did come to us with all the complex geometry and the very difficult pieces that they were having some challenges on how to install. So we helped out with some of that, and we also designed a lifting hook to install the panels in place. So again, you can see the effectiveness of level of detail when you're dealing with complex projects like this. So let's look at a few case studies that we've worked on. Here's Project Temple University. The people involved with the project here. This was a black granite, 5 3/4 inches wide by 2.5 inches thick. And it was strips, thin strips going up the facade. So we needed to create some kind of system to try and make it efficient. We created a grid and a connection system that aligned. And then it was supposed to be as random as possible. And I think we pulled it off, even though we did create a bit of a pattern in what we did. We designed a system that went back to the structure, and then a horizontal rail system, and then back anchors off the back of the stone, because the architect didn't want it. It was an open joint system, didn't want to see any connections through the joints. So all the horizontals that were crossing were painted black or very, very dark color, so you wouldn't see them through the shadow line. You can see the back anchors that were applied there. We had one load-bearing connection on each panel, and then we had slip connections on the other that just took lateral loads that could also take some building movement and thermal movements in the system itself. But you can see there's a pattern there, but when it was all complete, it was very difficult to read any pattern in the final installation. Here you can see the rails in place, the insulation that fit in behind the rails on the right, and then some of the stone installed. And there you can see the final product of the installation. Here's another private residence in Long Island, and just wanted to show this again, the technology today. The vertical walls there are 2-inch thick limestone, but we had many areas, much of the project was soffits on this, and a lot of square footage of soffit. And for the soffits, in order to keep weight down on the structure with all this cantilevered structure, we used the honeycomb reinforced stone panel, which is a 1/4 inch of stone on the face and then reinforced with honeycomb on the back. And that's what was used on all the soffit panels. So when it was finished, it didn't look any different than the 2-inch thick panels on the facade. Here's a courthouse we worked on in Portland, Oregon. It was a 40-millimeter limestone building, 17-story tall, all hand set. And the biggest challenge here was the high seismic zone. And we had a 3-inch story drift to design to. So we used a basically thermally broken vertical mullion system, very similar to you would use in a curtain wall application. We used the Kingspan insulation that fit in between them. And we had a very large movement joint at each floor level to accommodate, obviously, the seismic movement and thermal movements. And at the corners, we kind of separated each corner from the rest of the cladding and designed a pivot hinge connection on the corners that allowed, during the horizontal movement of the floor-to-floor movement, to allow those corners to pivot and rotate. So that was our concept, and we did full-scale mock-ups to actually simulate the condition. And we racked the upper floor from the lower floor 3 inches. It was tested for water penetration and dynamic water testing to ensure that it was still watertight after that movement. And we were very successful. You can see the panel rotating on the corner there as it was moving. And we actually ran it to 3 inches, let it come back, ran it 3 inches the other way, and there was no failure of any panels, no cracking or anything. They had the capability to move it to 4.5 inches, which we did. And a few panels cracked at 4.5 inches, but nothing fell off the facade. So we were very happy with that. Here's a few photos of the installation. Here you can see it going up with the Kingspan insulated panels in place. And that's the final product. I'll quickly go through another one here. I know we're a little tight on time. This is a project we're very proud of. It's an interior facade. Designed by Jaume Plenza. He's an architect, an artist that's very noted for his faces and human forms that he has in all different media. And this was a Meyer Gardens, a sculpture park. He was commissioned to do a new entry hall for the building, for the gallery and sculpture park. And his concept was to create 4 sculptural portraits celebrating young women of different backgrounds and nationality, celebrating versatility and humanity. So his vision was to create these 4 faces on each wall of the entry hall. And the concept was the 4 faces in vertical sections with the horizontal joints at random. And you can see some panels were right against the wall, others were 2.5 feet off the wall. Here you can see the model of the entire gallery here. They were color coded based on weight, size, and different parameters that were established, and they were grouped together for fabrication. So our role here was really, we got involved right at the very early stages with the architects, understanding limitations of the material. We did an extensive material testing on it. We were involved with engineering all the connections, how to anchor it back, and also how to install it, how to lift it, how to manage it, and all the logistics associated with that. So a pretty extensive testing program. The material was from Vietnam. It was called Absolute White or Flawless White. We tested the capabilities of an epoxy threaded rod because we needed to lift the stones, establish the center of gravity of each stone, and create a lifting device that the stones would always be in a perfectly vertical or horizontal position that can be placed easily into place without being on a tilt. Because you can see here, get an appreciation of the size of the pieces that we're dealing with. And they wanted to design it to a 2 millimeter joint, so an extremely tight joint. We had some panels as heavy as 7,000 pounds, and being on an interior application, the crane and structure was not able to carry those stones. So you can see on the panel being installed right now, we had to core out a bunch of stone to take weight off it. We were able to eliminate on some stones as much as 25% of the weight. So there was a lot of different challenges associated with this project. Here again, you can see the variance on the back of the stone and what we had to deal with to anchor it. So we created a steel frame system with vertical unistruts and a connection system that allowed for some adjustment. Here you can see the lifting device. Again, center of gravity of every stone was calculated and those rods were placed in a specific location. Here you can see the back framing that was designed for each vertical run. Here's the threaded rod connection that was used for adjustment in and out, and the unistrut gave vertical adjustments. And here you can see the final product of the 4 faces, and it came out spectacular. And here again, you can get a size of the scale of these pieces here. And his Joan Maplenza Utopia is our human landscape, a space to embrace humanity and our collective dreams. And we submitted this for an award, and it won the Grand Pinnacle Award of Excellence at the Natural Stone Institute Awards, which is kind of the best of all stone projects. So we're extremely proud of that, and that wraps up my presentation. I know I went really fast, and I hope I didn't go over time. Thank you very much.